These are the upscaled and colorized lessons of Alexander Lippisch. Lippisch was a pioneering German aeronautical engineer renowned for his significant contributions to aerodynamics, particularly his work on tailless aircraft and delta wing designs. His career spanned crucial decades of aviation development, marked by a persistent exploration of unconventional flight concepts.
When I explained to you in one of our last programs the generation of lift as a superposition of a rotational motion around the wing and the straight flow, we call it the translation, then you might have thought that these fabulous lift forces which carry these large airplanes with several hundred thousands of pounds through the sky, that these lift forces are in some way generated by a vortex motion, and that this vortex motion is necessary to make the lift of an airplane. Well, there are many other cases of such rotational motion in the fluid. And since the vortex is so important in many cases of fluid motion, let's talk a little bit about this strange fellow. Well, the last time I think I showed you some ring vortices out of this box. And well, since it is so nice, let's make some more of these. I think you see it better when I stand here and shoot it across our tunnel. Let's see. Now you see them? They go straight out, and it looks to you there as if you shoot just air through air. And when you look at them, you observe at once one very important law of vortex motion. See, the smoke comes out like a bullet. That means that all the particles of air which contain the smoke, or which are smoky air, stay together in this ring, which actually is nothing than a vortex ring. That means we know at once that if fluid is bound in a vortex, it stays together and goes through the other fluid as if it would be a solid body. On the other hand, when you look at this close, then you see that this rotation around a vortex is different than the rotation of a wheel. On a wheel, the outer peripheral parts move faster than the center. On the vortex, it's just opposite. The center moves fast and the outer moves slower. Now, how do we produce this? Well, let's think about it. Let's have a cross-section of this thing. This is a box, and there we have the bottom with a hole in it, which has very sharp corners. Now, we punch against this membrane, which we have back there, and then we produce a pressure wave which goes through here, hits these corners, and blows out a bubble of air, and then a bubble of air comes out here. This takes little particles which just were sitting here with it, and then new air has to flow towards the point where you have taken away these particles. So this motion and this motion produces a spiral motion which makes a kind of a mushroom, and out of the mushroom finally comes your ring vortex. We have made some high-speed pictures, some slow-motion movies of this generation of the vortices. And let's now look at these pictures. First, we see a front view of the box. And it's very interesting to observe first the radial motion of the air, and then the bubble is formed and comes out as a ring vortex. In the next picture, we see the same process from the side. And since we have a membrane back there which is elastic, the bubble jumps in and out first before it finally travels away as a ring vortex. So here we have another tube where we have another kind of a membrane on it, so this doesn't happen, and it looks like an atomic explosion, actually. But the most interesting view is to see it from in front, which is this picture again, and observe the vortex formation before it comes out. This is most interesting, and I think it's only shown in this high-speed picture. You never can observe it with a bare eye. Now, what we have seen here was that the formation depends on a flow across a sharp edge. And behind the sharp edge, the vortex is forming. Then we remember that we saw this once on an inclined plate. Actually, the formation of the wingtip vortex is nothing else than it hits the sharp edge of the wingtip, and then the flow rolls over it and forms this wingtip vortex. Let's look at this thing again in our smoke tunnel. And we have, in this case, we have just a part, the ending of a flat plate in it, and when we turn the blower on and we have some smoke, then we can very well see again the formation of this spiral vortex from this corner where the flow actually stalls away and new air from the side moves in and forms then this spiral motion. You see it here very well. And when you look at it from the side, then you can actually see the three-dimensional development of this spiral motion. Now, you know, we have made these vortex rings and the straight vortices in the air. And you might think, can you do that also in other fluids, for instance in water? Well, I will show you. You can actually do the smoke rings in water, and we have here a water tank. We don't have fishes in it, but we have a hole at the center, and underneath of this tank we have a little container with colored water. We have some ink in it, and with a membrane underneath. And when I push this membrane, then we make the same smoke rings here, the water rings, as we did it in air. Now watch this. See, I push it up and let it go slightly. And there is the smoking. Do you see them? Another one. Another one. When I make it a little bit more violent, then you see that it even jumps out of the water. What's this? Oh, this. Now we don't want to color this all up, because then we don't see our rings anymore. But I will just make one more. You see? Therefore, we can make these vortices also in such a dense fluid as the water is. Now, when you look at the rings and you see that they jump out of the water, at least at the center, you think about what sense of rotation is in there. Let's talk about this for a moment. See, we have actually here our bottom, and there's a hole in it. And now when we push, then the water comes out of it, and as I told you, forms first a bubble, like this, a mushroom, and out of the mushroom comes finally this ring, which travels up there as a true vortex ring. The center of the vortex is somewhere here, and the highest motion is in the center. Now the sense of rotation will be then this. Since we push this way, we have a rotation which goes around this way and this way. That means the outer turns back and the inner goes up. And when we now hit the water surface with such a ring where the rotation is this way, then we have a water column which now jumps out of the water here. Since we have in this center, we have the velocity against the water level, and the other ring disperses along the water surface. Now, you have probably yourself observed in water another type of a vortex. You know, when you open the sink of the bathtub, let the water out, you often observe that there is forming a kind of a funnel, and that the water begins to rotate and form such a funnel of air and surrounded by rotating water particles, which actually forms a straight vortex going into the sink. I think we can show that also here in our water tank. When we let it out, then first, due to discontinuous motion, due to some disturbances which are in there, the water which all wants to flow towards the center misses this center a little bit, and due to this, a rotation begins, which finally forms this funnel. Now it slowly begins. You have to wait a little bit, and this depends on the level of the water when this vortex actually develops and the size of the opening. I can see from here now that the rotation begins to form. And pretty soon you will see that due to the low pressure, which is in the center of the vortex, there will develop a little dip in the water, which shows us the beginning of the vortex formation, as it is now. Now you see it beginning, and then it pulls down. You see it now coming down and going towards the outlet. See now? And this gets stronger and stronger. You get a little wet with these experiments, but don't bother. And you can see now this vortex funnel very clear going down into the sink. The rotation in the center is quite strong. Well, let me explain to you a little bit more how this comes to such a rotation. And while it runs out, We can see a little bit still. We will talk about the cause of such a vortex. The main thing is that you have to have a sink. That means what is first with the formation of the vortex? What is first, the chicken or the egg? And what is here the egg and what is here the chicken? Well, the chicken is the vortex, and the egg is a low pressure area where everything flows to it. Now, when it does this, when we have this hole in the center, we pull the plug out, then all the water wants to go towards the center. Because the pressure here is lower than the pressure in the surrounding water. Since we pulled the plug, at this point, we have no water pressure from above. Now, theoretically, these lines and these flow lines should all come into the center. But due to little disturbances which are on the floor and which are in the water anyhow, some of the particles will not have the straight line into the center, but just miss it a tiny bit. Now, when one of these lines misses this point and shoots over here, well, then it is sucked back into it, and so this rotation stops. And then, since this missed it, the other particle which wanted to go here comes also around and does the same thing. And then finally all of them do this, and there we have the vortex. Due to the courtesy of the Hydraulics Research Institute at the State University of Iowa, we have some nice films of such vortex formation, and we can see them here, especially a film which is taken from above, where you look to the vortex formation from above, and you see very well in these films the velocity distribution in the vortex. You see where the center rotates the most, and towards the outer, the rotational velocity gets smaller and smaller. Now we see here again the development of the funnel from the side view. First, a very fine line which gets wider and wider when the rotation increases, here due to the gravitational forces which push the water out through the bottom sink. And finally, we have a big funnel with a very strong rotation around the center. The low pressure at the center is so low that we have, instead of water, we have here air in it, because the water level itself goes down up into the sink. Now we have put some dye into the funnel, and you might see the flow around the funnel itself made visible by putting some dye into the fluid. There's a picture where we see the outer motion of the fluid. If you see these experiments with the water funnel, you might remember that you have seen this too in pictures, or even if you are from the south, in nature, as a big tornado funnel. And you might think that there is some striking similarity between the funnel of the tornado and this outlet vortex in a water vessel. I think before we talk about this more closely, let's look at some of the pictures which we got about the tornadoes, where we can see them and observe their formation. Now, besides of this most violent of all windstorms, the tornado, which represents a vertical vortex column, we can observe in nature also horizontal formation of vortices. And I have here an experiment built up where we can see a special vortex formation due to the fact that we have a hot plate underneath on the bottom and a very cold one on top. And when we let the flow go through this channel, then due to the convective motion, the hot plate heats the air on the bottom, the thing goes up, the air goes up, hits the cold layer on top and returns again. And you see in this a row of counter-rotating vortices. Let me explain just shortly this little apparatus. We have here a box here with a glass wall on top, here on the side, where we can look into the channel. There is the channel itself. On the top we have a metal plate with dry ice on it, so that's real cold. From underneath we light it and have a glass wall, so the light comes on the glass wall and heats the glass wall so that the glass wall is hot. And then we suck this off by a blower. When we turn on the blower, then we can see this little noise, smoke develops. We have to look then into this thing from here. And when we look this way in, then we can see a picture which looks almost like this. There we have the hot plate. It's hot. That's cold. And there we have counter-rotating vortices. So the air goes here up, there down, here up, and there down. If we have this in nature, where the air goes up, clouds are forming. And we see long, mile-long cloud streets forming when we have cold air on top, a very cold layer on top, and the ground is heated by the sunshine. The energy which makes all these vortices comes in this case from the heat, and in the atmosphere also due to the layers with different pressure and density. You can observe also a vertical vortex forming from the ground, which we call the dust devil. And we have here a small glass box where we can make little models of such dust devils developing from the warmer surface of this box. It is enclosed so that we actually can see better how these vertical vortices, these dust devils, develop. The main thing is that we have a very warm layer on the surface itself. And when it rolls over, due to the slow motion, it begins to roll, and then a vertical vortex spools out of it, as you see it very well in this box. The warm layer is what we see here as a smoke. And all these spooling up lines are actually vortices which are produced from this warm air going up and rotating as it goes up, because the air can only go through other air if it assembles into a vortex. And you see here very well that every of these fine lines is actually a vortex. Now you see it very near to the formation and very near with the camera, and we can observe more distinct this rotational motion. But let's get back to our aerodynamics. We get too deep into methodology. A vortex which we saw was the wingtip vortex. And here's a picture of a cross-section of such a vortex which we took in the 3D tunnel. Isn't this a striking similarity to something which you might have seen sometimes in pictures from the great telescopes which survey our stars in the sky? When you look at the picture of the wingtip vortex formation and you see a picture of a galaxy, of a spiral nebula, you see that something is similar in both pictures. I don't know what it is, and I doubt that we have a clear explanation of this similarity and whether there is any spiral motion in the sense as we observed it here. But you sit here on such instruments and apparatus and see these strange things develop, and you think it over, and you finally end up that anyhow many things stay unexplained to you. As the great poet says, mysterious even in the light of day, may never nature of her veil be freed, unless she willingly unveils to you nothing you thought from her, with lever or with spoon. Goodbye, and auf Wiedersehen. Come on, come on, come on, come on, come on. There it is. You see a mechanical bird. And, well, when you look at it, the basic system of flying is here the same system as the bird has it. The inner part of the wing gives a lift, and the outer part of the wing propels this little aircraft model. Now, to explain it a little bit more to you, you see there is a crank shaft in there, and with two connecting rods, we move the wings. See, when I now wind it up, I just push one of the connecting rods, and then the wings go up and down. So, and when I have wound up enough of these two rubber bands, here's one, and there's another one, this is a motor, then I can let it go. It's a little tricky, you know. And the bearings are all made from small glass beads, so they have practically no friction. You see, now I can let it go, and it flies nicely around like a tamed bird. Well, here it is. Now, before we go further into thinking about bird flight, let's explain at first how ever a flapping motion of the wings, as it is all done by the flying animals, how this can produce propulsion and lift. Now, as you see it here in a very simplified form, the wing goes just straight up and down. And while it moves forward, this up and down motion and the forward motion will give a kind of a wave trajectory, what you call a sinusoidal curve. Let's have it here on the blackboard. So, Let's begin with the wing in the upper position. This might be our center line. And here we have the wing in the upper position, and then the wing goes down to here. This is a downstroke. And from here back to the position as we began there, this is the upstroke. What happens? While this wing beats down and goes forward, the air will blow from underneath towards the wing. And when we think that we have here somewhere our wing section, then the blow comes from underneath and gives us a force which is in this direction, so that we have lift and forward thrust. Now here we have the condition as we have it normally on any wing, stiff wing, just the flow coming from in front, and we have a little drag and we have medium lift. Now when we pull it up, then in this position the wind which the wing feels comes from above, and we have actually on such a model we have a little down lift, or practically no lift at all and only a small drag, so that during the downstroke we produce high lift and forward thrust. During the upstroke, the trick is to move the wing in such a way that we don't have much drag and still maintain a certain amount of lift. Now, this is done with the bird in such a way that its center part of the wing doesn't move much up and down. This is a lifting part, while the upper parts, the outer parts, they have a much larger motion and they work as propulsion. And in this way, this model represents the same system as you have it on a flying bird. The center part gives the lift and the outer part produces the thrust. I will just hold it while it flaps up and down. You see one other thing, very clear. It is necessary that this outer wing twists, because while it goes down, the downward motion on the tip is much faster than on the hinge point, where there is practically no downward motion. Therefore, the wing, while it goes down, has to twist like a propeller twists. And you must think that this beating down is a part of a motion around a center point, and our propeller is in some way comparable with the outer part of the bird or the insect wing, because there he does the same thing, but he cannot do it all around. So he has to reverse the motion and beats back, and while he beats back at insects, he also gets propulsion. With birds, he pulls it back more in a way so that there is practically no drag with this wing because he folds it in. Now, this is one aspect of the flight. And therefore, when you think that this simple up and down motion has this difficulty that this upstroke is quite long, and you would have a long time drag in it, you could do it easier in moving the wing not just up and down, but moving it a little bit in a circular motion. Then you would change this in such a way that you have a longer downstroke and a short upstroke. And while you have the downstroke, you have all the velocity which is needed to make the lift and forward thrust. In the upstroke, you have practically no speed because you pull the wing backwards. And in this way, this wing is brought into its working position in the downstroke by the most efficient way and the way where the drag is the smallest. This method of rotating the wing we see on all flying animals, as well on the insects as on the birds. We have here a small model of a, well, bird, or what you might call it, in this tunnel. And by some tricky mechanics, we have made the wings flappable, so that with a little motor, as you see it now, we can oscillate the wings with a pretty high frequency and observe now the action of these flapping wings on the flow around the model. We can even see it better if we have a high-speed picture which we made from this model. These are extremely interesting pictures. You see, since we oscillate the wings, the flow behind this birdie is also pulsating. And we see that while it beats down, every time a tip vortex is generated. While when we would have steady wings, then this tip vortex is a steady vortex. But here we have a row of single vortices emerging from the tips of the wings. Now, if you investigate the flight in nature and observe the different types of flying animals, like the insects, the flying fish, the birds, and even some flying mammals, you might wonder why there is a difference in the texture of the wings, and why, for instance, at small animals like the insects, the wings are designed and built in a different way than it is, for instance, with a big bird. This is important to know, and it is mainly due to the fact that the resistance, the friction on surfaces at different sizes and speeds follow a different law. This can be compared if you think about what we call the Reynolds number of this flow condition, which is just a comparative number to see whether certain flow which you have investigated here, and you would again investigate here, whether this is made under a similar condition. And this similarity law tells you on the other side what type of a friction on this surface you would have. Now we have here a chart, and there we have plotted these laws as they are physically and theoretically established. And we find this, that there are two different types of friction on a surface. One friction, which we call the laminar friction, where the air goes smooth over the surface in parallel layers. And another friction, which we call the turbulent friction, where the air breaks up, as we have seen it, you remember in the program where I showed you something about the drag on wings. Now, the laminar friction follows a line in this diagram like this one. The turbulent friction follows another line, which goes out here. And you see one important point, that in this range, at very low Reynolds numbers, that means at very small speeds and very small lengths or sizes, the turbulent friction is lower than the laminar friction. And above this point, the laminar friction is much lower than the turbulent friction. Therefore, if you want to make an efficient flying object in the small size, you have to make it so that it is producing turbulent friction on the surfaces. And if you have it in larger sizes, then you have to reverse it. And you have to make it smooth so you get as much laminar friction as possible. Therefore, when you look at an insect, you are always wondering why it has so many hairs on it and is so rough. It is rough because it has to be rough, since in this size, the viscosity of the air has a much stronger influence. And if you would think you have to move in something quite viscous, well, then you have to paddle around so that you get the stuff moving, otherwise you wouldn't get through that sticky stuff. And this is what this little insect actually feels, and therefore he makes it rough. While when you are way up there, as the birds are, especially the larger birds, well, then you have to be as smooth as our airplanes have to be. Therefore, if you investigate all these things, you have to understand it. And you have to see one thing, for instance, that if you take such an insect as a model of something which you want to build in larger sizes, then you have to be careful, because you could not just take this dragonfly, for instance, and enlarge it 10 times and then fly it. It wouldn't fly, because he is then, your model, in a complete different region of Reynolds number than your original was, and therefore different laws of friction govern this motion of the air around this wing or the body. Now, let's look at some of our wonderful pictures which we have from insect flight. First, we see some silhouettes of hovering bees and flies and wasps, which was given to us due to the courtesy of Professor Chadwick of the University of Illinois. Here you see, for instance, a bee flying, and since we mainly observe here the hovering flight condition, we see that this little animal moves its wings more or less in a horizontal plane forward and backward, so that the propulsion which is now done by the wings works like a propeller, which you now put forward and backward. Instead of running it around, you just change the pitch from the positive to the negative part and moves the wing forward and backward, and in this way you get the same lift as you would give it, for instance, on a helicopter. There is a wasp flying, and you see the interesting attitude of its rear body, which is this part which is stretched out so high. So he stabilizes the flight with this tail. This is now the dragonfly, which is one of our best flyers. All these pictures now are taken from animals which are pinned to some little stick, or what you might think. And in this way, what you observe here is not quite a free flight condition, but you still be able to see how he moves the wings. And when you observe it right and clearly, then you see that these wings are not moving just straight up and down, but they are moving mainly from a position of rear up to front down. Now we have another very interesting insect film, which is the flight motion on the wings of a drone fly, which was given to us by the Sperry Gyroscope Company, who was interested to see not only the motion of the wings, but especially to see what a small little, what I would say stick would do, which this animal has behind the wings to keep its equilibrium. It is thought that this small object, which we call a halter, would work as a gyro works, since when you oscillate a weight on an elastic stick, then this oscillating stick would give to its base the same signals, the same moments and forces as you would get it from a gyro. And in this way, the fly stabilizes its flight. Now there you see a close-up. In front is the wing, and at the rear we see now the head of the halter, which is a word which is not a halter, but means a leaping weight. And behind the wing, in a groove, we see that this little object is moving up and down in a phase shift between this and the wing itself, but actually at the same frequency. When we now come to the pictures of bird flight, we first have to remember that there is a large step from the sizes of the insect to the size of the bird, as we saw it in this diagram. And what we have to observe mainly is that the motion of the wings resembles in some way, you could say, a swimming motion in the air, where the outer portions of the wings are rotated in a cone surface. Now, to see this probably a little bit clearer, we have there a model in the wind tunnel where we can simulate a rotating motion of a wing section. Now watch this. Here we have it. And you see when we rotate it, then while the thing goes around, it adjusts itself to the local flow condition. We see it much better if we look at a slow motion picture, which we have here. Here we have the wing in the upward position and begin with a downstroke. We see that it produces quite a bit of lift since the flow lines are deflected. Now while it goes back, it loses speed because it has not much speed against the flow, and while it moves upward, it's only adjusted so that it makes as few drag as possible. And again, the downstroke begins with a large lift. Now, to see the bird flight, it is necessary that you make the pictures with a slow motion camera, and that is what we see here, where several of the pictures are taken with about 64 frames per second and the other ones with about 130 frames per second. So all the time our motion is slowed down. Here we see a takeoff of a duck, which needs quite a bit of run along the water to get off with this heavy wing loading as the duck has. Observe the rotating motion of the wing tips. This one is a landing, and you see one thing. The bird can do not only forward cruising flight, but it can also do with its wings a stationary flight. That means hovering. This is a big difference between the wing of the bird and the wing of our airplanes, which cannot do this. And the bird, that means the nature, has solved this problem in the most elegant way. There we see some geese, and observe how they take off just from the spot where they sit. They are real VTO aircraft, I would say. Now we have some pictures of the gulls, which are one of the most elegant flyers in nature. You see one thing, these seabirds have a much higher aspect ratio. That means they have a narrow wing and a large span. First of all, there are no obstacles like the trees and bushes as it is on the country. They fly out on the ocean. On the other hand, they use quite a bit of soaring flight where a high aspect ratio is necessary. Here are some pictures of gannets, which are also very good flyers. They partly soar and partly we see them in flapping flight. Observe here the motion of the outer wings, which are here the propellers of these animals. The inner part is used for lift mainly, the outer part for propulsion. One thing also is important to observe, that they don't use their tail while flying. This picture is a hawk in flapping flight. You see very well the rotational motion of the outer wing. Now comes one of the masters of flight, the man-of-war bird, which mainly is a soarer and uses the flapping flight only quite temporarily. But you see the twist of the wing while he beats down very well in this picture. This is a spoonbill, which shows us again the motion of the outer wings very distinctively. But these are not all the secrets of the flight of the animals. And you often think, why isn't there a way for us to learn more about this elegant and most fascinating method of flight as it's done in nature? You might think that we don't need it anymore, but we still can learn many things when we translate our knowledge from the observation of nature into the technical application as man has to do it. Everybody of us is thinking about such things if he sees a bird flying around his house, if he is out on the shore and the gulls are flying around his ship. And as the poet said, in the heart of every man will feelings surge above him and beyond, when high up, lost in lofty blue space, the skylark sings her glorious song. When over steep and jagged heights, with wings outspread, the eagle soars, and over prairies, over lakes, the heron flies to distant shore. Goodbye and auf Wiedersehen. When in October 1947, Major Jaeger, with the experimental rocket plane, the Bell X-1, took for the first time the speed barrier. A new era of flight was born. The flight in the range beyond the speed of sound. This is a picture of this aircraft, which is the first supersonic aircraft ever built. Now, you might ask the question, what has the speed of sound to do with flight? And why have the scientists all the time talked about the speed barrier of the speed of sound? Well, as you know, the speed of sound is roughly 770 miles per hour. And if I here make a small disturbance, a noise, I make lots of noise, but I clap the hands here like this, then this sound travels away with a speed of 1100 feet per second. And if somebody, for instance, stands away 13 miles, he would hear that clapping just 1 minute after it happened. Now, what is sound? Sound is the pressure, the pressure waves which are created by such disturbance. And the speed of sound is the propagation speed of such pressure waves which go through the air. That means, well, since it is the speed of pressure propagation, and since our aircraft are supported by pressure fields, this speed is also the propagation speed of the pressure field around an aircraft. Now, let's imagine this. Let's imagine there is an aircraft flying a straight course just horizontally ahead. And as you know, it's supported by pressure underneath the wings, suction above the wings, and all this other thing around fuselage and so on. Now, if you imagine just a little tiny particle of air which is ahead of this aircraft. While this aircraft comes along, its pressure field is propagated, and this little particle gets a tiny signal that there is coming Captain Smith with a big airliner, and the little particle, well, polite as air now is, begins a motion to get fine and smooth over Captain Smith's airliner. Well, that's all right, as long as this airliner flies below the speed of sound, below the speed of the propagation of its pressure field. But if now Captain Smith comes with a slick supersonic airliner, well, then this little particle doesn't get any signal before the airliner is there. And suddenly there is Captain Smith and the airliner and the little particle. What happens? A collision happens. And well, it's not very serious because air is not a solid matter, and it is compressible, a compressible gas. And due to this coming together, the air is compressed through a shock wave, and all the particles which are now hit by the wave of the airplane will get a sudden compression shock and a sudden deflection. Therefore, in the subsonic range, the flow field is uniform all over. And in the supersonic range, we have a complete difference. Now, let's go to these charts, which might explain the thing a little bit more clear. You see, here is Captain Smith in the subsonic range, and the pressure waves which are created by small disturbances go out all over because they run out the speed of the airplane. They are far ahead of him, and the farther he flies, the farther ahead are these pressure waves. But if we think now of a supersonic speed of the airplane, then these waves which go out in circles would not reach any space which is on the sides or ahead of the airplane outside of this cone, which is formed by the pressure waves which are exerted from this airplane flying at supersonic speeds. And there is a very distinct cone formed in which only the air can be under the influence of the pressure field around this airplane. Now we call this cone angle, this cone, the Mach cone, and we call the ratio of the speed of sound with respect to the speed of the aircraft, we call it the Mach number. So that if somebody flies, for instance, with a Mach number of 2, that means that he flies 2 times the speed of sound. That would be roughly 1,500 miles per hour. Now there is another very interesting and significant difference between the subsonic and the supersonic flow. When you think, well, you want to make high speed through a nozzle, then you might have a big tank and pump it up and then have a little nozzle and let the air out. And the more you pressurize the air in this vessel, the higher the speed will be. Yeah, up to a certain point. You will find out that you pump it up as much as you want and you don't get out of this opening more than the speed of sound. Therefore, we have to devise a new type of a nozzle. The first man to design such a supersonic nozzle was Pierre de Laval, and therefore we call a nozzle which is now first convergent and then divergent a Laval nozzle. This is necessary because due to this increasing in speed and decreasing in pressure, the density of the air gets lower and lower, and therefore beyond the speed of sound, the density decreases more than the speed increases, and we have to open up. And in the supersonic range, acceleration means a widening of the streamlines, and deceleration to get the streamlines nearer together. In the subsonic range, it's just reversed, as we know, because when we want to make more speed, then the streamlines have to come together nearer by. And diffusion means deceleration. Therefore, all these geometries of the flow fields are completely changed. In the subsonic range, we see that the flow is completely symmetrical. And when we neglect the friction, the forces are in balance. But when we think about the same pump and a supersonic flow over it, then we see at once that we have in front a pressure on the surface and at the rear a suction on the surface, which makes since this is the pressure force, this is the suction force, which makes a component of the forces in the direction of the flow, a drag component besides of friction drag. This is the wave drag of the supersonic flow, which then necessarily has a strong influence on the efficiency of the supersonic aircraft and diminishes the range and makes it necessary that such aircraft have large power and a large fuel consumption. On the other hand, as we see it here, also the pressure distribution on the wing changes considerably, and we have a shift in the center of pressure, which was here at the first quarter of the airfoil, and here is almost at the center. This makes a stability problem in the supersonic range. But let's look now at some pictures which we have from the flow in supersonic wind tunnels and in nozzles. They are made by the so-called Schlieren method, and what we see is the density changes in such flow. These pictures are made available by the National Advisory Committee for Aeronautics in Langley Field, Virginia. We see a thin airfoil in the transonic range. That means going from the subsonic flow into the supersonic flow range. At the present time, we see what is called buffeting. That means we have a formation of oscillating shock waves on the both surfaces. Finally, these oscillating shock waves come together into one straight shock, which is now beginning to form at the rear part of the wing, and with increasing Mach number. You see it from the finger, which moves down on the scale and which is now in the range of something above 0.9 Mach number. The shock travels backwards towards the trailing edge and finally forms an oblique shock, so that the whole flow on the surface of the wing is supersonic, which you also see from the slim Mach waves which are generated from the surface of the wing. Now we reach the Mach number 1, and the flow is completely supersonic. Another interesting effect can be seen in the jet stream from a rocket or a jet engine in the supersonic range. You see waves forming in such supersonic stream, which is here on the first supersonic aircraft, the Bell X-1. And we see it now here as an experiment in our laboratory, where we have a nozzle on the left-hand side. The jet stream comes out with supersonic speed, and the dots we see are the waves which are formed in this jet stream. The more we go down to the sonic speed, the smaller the wavelength gets, and finally our stream disappears completely when we have subsonic flow in this nozzle. Now, when you think of all these problems which arise from the flight in these high-speed ranges, then you might realize that the original concept of the aircraft as a powered glider is probably not the final solution of the aircraft for the use of human communications. See, in the meantime, while we were working on these high-speed problems, a new type of an aircraft came up. This was a helicopter, which could fly without any speed. And it has taught us a very important lesson, that such a feature to hover and to raise from just a tiny spot on the ground and to come down on it is so important that, well, many other things are not important with respect to difficulty of obtaining such features. So the question is, can we combine this low-speed aircraft with our high-speed aircraft in one new conception? And when you think about it, you come to the conclusion that this certainly might be possible, but that we have to have then an aircraft which is not derived from the natural prototype, but which we conceive from scientific and technical information. A man-made flying machine. Now we have begun with this work, and to distinguish it from the aircraft, the powered glider, which is called the aeroplane because it has planes, we call such types an aerodyne, a body which is dynamically lifted. And this dynamic lift is made by an internal flow system. Now, we are just at the beginning of such development. And I can show you here one of the first models which we have developed from this type of an aircraft, so that we might show to people what we mean with this development. You see, this is a small model which is lifted by a row of 4 shrouded propellers. You remember, as I have shown them to you in our propulsion program. So in each of these holes, as you might call them, is an electric motor which drives a little propeller. The stream which comes out and lifts the thing goes over certain control surfaces which are down there. And these are stabilized by a gyro system, and I can also control them from a seat. The electric power comes in through this cable, since we cannot carry batteries in such a thing. And also the control signals which I give from the seat go also through the cable. You see, we have an undercarriage, and when I have good luck, then I can take it off and bring it down. Now this is the seat, and you see I have a normal control like in the pilot seat, and from here I can switch in the power for the gyros, as I do it right now. And then when I switch in the power for the engines, the thing will take off. Now we will try another flight with this model. You know, this model was designed about 4 years ago, and it actually serves the purpose to show that you can stabilize a flying body in the low-speed range. And this was the purpose of this model, and we obtained this purpose by using certain gyroscopic action to control flaps to stabilize the thing in flight. Now, let's try it. Now, the models I have shown to you in flight are just the beginning of something which has to be developed into an efficient aircraft type. To give you a little imagination of what might come of such a development, we have here in the tunnel a model which might illustrate the use of such internal flow systems which give lift and forward thrust and can be used in the flight at no speed as well as in the supersonic speed range. We come now to the end of our program, and I want to thank all of you who have watched The Secret of Flight go on the air. I want to thank also the Office of Naval Research and the Collins Radio Company, who have given the permission that we could use this smoke tunnel and some other equipment. We have tried to give you a short glimpse into the wild field of aeronautics. And we hope that we have raised your interest on several problems in the field of aviation. Our time was certainly short, and we couldn't show you many things we would like to. But nevertheless, the few examples we could demonstrate were, as I hope, of a more general interest and gave you the idea of what might come out of this development in the future. See, the work of the scientist and of the engineer in this field is certainly not an easy task. And it is necessary for the evolution of new principles and of new knowledge, that this is carried on from one generation to the next. Despite of the tremendous progress which has been made in these first 50 years of aviation, many problems still await their solution, and every day opens up new fields, new views, new aspects in this new science. As you know, today, aviation serves mainly and to a large part as a defense of our freedom and as a deterrent of war. But besides of it, aviation has flung his arms around the world to bring men to men and to create mutual understanding and new friendships. You see, to break the speed barrier was a scientific and technical problem, but this may serve at last to solve a great human problem, to break the barrier of fear and distrust, and to bring love and happiness to all men. Thank you and goodbye.